Okay, so what we're going to look into today is transformers, or R transformers. And although we've already discussed it a little bit in the course, let's just be thorough. The purpose of the transformer is to change voltage levels. The purpose of the transformer in power systems is to change voltage levels either up or down. We have generators. They are physically limited in the magnitude of the output voltage that they can produce. We know that there are benefits to transmitting power at high voltages and low currents, particularly in the reduction of I²R heating loss in the conductor. We know that there are some negatives associated with large voltages, primarily safety requirements and insulation requirements of the wires and the spacing requirements of the wires. So we tend to use high voltages and low currents to send power over long distances when we have the advantage of being able to isolate those from people and from trees and things like that using large transmission lines. We are able to convert the medium level voltages output from generators to the high level voltages necessary for high voltage transmission using these transformers. That would be a step-up transformer. And then when we get the voltages to substations where they need to be in close proximity to humans and physical devices, we then need to reduce those voltages. We do that using a step-down transformer. And before we get into the concept of transformers, we need to go ahead and we need to look again at the concept of inductance. So what we shared before was that if we had an inductor, it had a current flowing through it. It was given a value of inductance L, measured in Henry's. Current was measured in, and then of course there was a voltage applied to it, measured in volts. And what we showed for this was that the voltage across the terminals of the inductor in terms of time is equal to the inductance times d I of t dt. So what that says is the voltage across the inductor is equal to the inductance times the time rate of change of current. And how we wrote that in the frequency domain was we said x sub L is equal to omega times L, the frequency of that AC voltage and current waveform, and that allows us to write V is equal to I times omega L. So the voltage across the inductor in the frequency domain is I times omega L, or I times the inductive reactance X sub L. And the reason I bring this up is that we know that the property of inductance, this L, has to do with the magnetic field that gets induced in this coil of wire here when current flows through it. If you don't remember that, I encourage you to rewatch the videos on inductance, but basically what happens is this current flows through the inductor and induces a magnetic field. The time-varying magnetic field establishes a voltage inside the inductor that opposes this voltage here, and we get a reduction in voltage across the system, I times the frequency omega L. We know that the faster that this voltage oscillates back and forth, the bigger the frequency, the bigger the effect of this inductance, and therefore X sub L gets larger as a function of frequency. Well, this is better called self-inductance. We ran a current through the inductor. That current established a magnetic field that established an electric voltage that opposed the original voltage in the first place. So this is self-inductance. This magnetic field that gets emanated from this guy can also influence other circuits, and that is where the concept of mutual inductance comes into play. So we're going to look at this concept next called mutual inductance. So in mutual inductance, really what we're concerned about is we've got the following circuit: R1, L1, L2, R2, and what we'll find out is that these two circuits get linked together by the magnetic field created in the two inductors. In this case, the voltage induced in the second circuit here, L2, can be related to the time-varying current in the first circuit by a parameter known as mutual inductance, M. So this circuit represents two magnetically coupled coils. We label the self-inductance of the two coils L1 and L2, and the mutual inductance between them is labeled M. The double-headed arrow adjacent to M that I drew indicates the pair of coils with this value of mutual inductance. The reason we note this is circuits can contain more than one pair of magnetically coupled coils. The different coils will have different M values associated with them. The different pairing of coils will have different M values associated with them. So this mutual inductance indicates the inductance between two paired coils. In this case, L1 and L2 are the only ones, but some circuits will have more than two paired coils, and so there'd be multiple M's in that circuit. And the arrows show which two circuits are linked together. So typically what we do to analyze circuits containing mutual inductance is we use mesh currents. We'll assign a current in the first mesh, I1. We'll assign a current in the second mesh, I2. The directions of those currents being kind of arbitrarily chosen. What this results in is that because of the mutual inductance M, there's two voltages across each coil. There's a self-induced voltage due to the current flowing through it, and there's a mutually induced voltage due to its magnetic coupling with the other coil. The self-induced voltage is, as we showed up here, I omega L, and the mutually induced voltage is going to be the product of the mutual inductance of the coil and the current in the other coil. So let's consider the coil on the left hand of the figure that I just drew. It's got a self-inductance of L1, and therefore the self-inductance voltage drop across this is V self is equal to I1 times L1 times J omega. So it's the current times the inductive reactance, which is J omega L1. So that's the self-induced voltage across the coil. The mutually induced voltage, V mutual across that coil, that's I1 times J omega L1. The mutually induced voltage across this coil is going to be I2 times J omega M. So there's two voltages across this coil right here. The self-induced voltage, I1 J omega L1, that's the same as we saw for the normal case of the inductor. And then there's a second voltage due to the magnetic coupling with L2. That voltage is I2 times J omega M, where I2 is the current flowing through L2 here. So what we haven't established yet, though, is the polarity of these voltages, and that's actually a little more complicated than it is in a normal circuit. Due to the way that the inductors are wound, there can be multiple voltage polarities it depends on the coil construction. We're not going to get into actual construction of the coils here, but what we are going to do is introduce what is called the dot convention. And in this circuit, I'm going to put a dot here and a dot here. And the dots in a mutually coupled or a mutually induced circuit, or a circuit with mutual inductance, however you want to say it, the dots are used to keep track of polarities via the dot convention. These dots carry our sign information, and what they allow us to do is really ignore the physical construction of the inductors. So we won't get into that. We're just going to stop at the level of the dot convention. So basically what the dot convention says is if a current enters the dotted terminal of a coil, the reference polarity in the other coil is positive at the dotted terminal. So what this is saying is because I1 flows into the dotted terminal of L1, my reference current flows into L1, that the voltage induced across L2 by the mutual inductance is positive at the dotted terminal. So we say that when the reference direction for current enters the dotted terminal, the reference polarity of the voltage induced in the other coil is positive at the dotted terminal. Another way to say this is when the reference direction for a current leaves a dotted terminal, the reference polarity of the voltage that it induces in the other coil is negative at its dotted terminal. So for the most part, what I'm going to do is I'm going to provide, well, actually I will always provide you with dot marking in the circuit diagrams, and the skill you have to develop is to be able to write the appropriate circuit equations giving your understanding of the concept of mutual inductance and the dot convention. We're not going to worry about figuring out where to place the polarity of the dots if they're not given. The only way to do that is by examining the physical configuration of the actual circuit or by being able to test it in a laboratory setting. It has to do with the way the wire is physically wound in the inductor. So that's a little bit beyond the scope of what we're going to do in this class. So let's draw ourselves a new circuit. It's going to be the exact same circuit we just drew. We just want to apply the dot convention to it. We've got our voltage source here. We've got a resistor R1. We then have an inductor L1 here. And we're going to say that the dotted terminal of L1 is right there. And then we've got our second inductor, it's L2. Its dotted terminal is going to be the bottom. This right-hand side of the circuit has a resistor associated with it, R2. Oh, I forgot to label the voltage source, it's VG. Again, the mutual inductance between the two coils is just given by M, which is in henries, and we're going to just establish two reference currents, I1 and I2. You know what, I'm going to move those outside just to give myself more room inside of the circuit. So that's the circuit analysis. What we want to do is we want to go ahead and sum the voltages around each of the closed loops. So let's start on the left-hand side of the circuit. If we just sum the voltages, we know we've got a voltage rise, so that's minus VG. We've got the voltage drop associated with R1, which is plus I1 R1. We then have the voltage drop associated with the self-inductance of L1, which is going to be plus L1, well, let's write it as plus I1 times J omega L1. Now what we have to do is take care of the mutual inductance. We see that the reference current leaves the dotted terminal of L2, the reference current being I2. So the voltage that's established across L1 is going to be negative at the dotted terminal here. So we're going to get a voltage established minus plus, and it's going to be M times J omega, and that gets multiplied by I2. That's the voltage drop associated with that. So if I incorporate that into my circuit model, I get minus I2 times J omega M. Now we need to write the sum the voltages, write the equation for the sum of the voltages around the left-hand or the right-hand circuit. So we've got the current leaving R1 or R2 here, so that is I2 R2. We then have the current going through L2, it's going to be plus I2 times J omega L2, just as we had done previously. Now we have to account for the voltage established across L2 due to the mutual inductance. The reference current establishing that in this case is I1. I1 enters the positive terminal. Here we see I1 coming down here. Here's the positive terminal. Therefore, the voltage it establishes is positive over here. So that's minus plus, and its value is I1 J omega M. So now we see that this is a voltage rise in the right-hand circuit, so we get minus minus I1 times J omega M. And so now we've been able to write the Kirchhoff's voltage law using our mesh currents for both the left-hand side circuit and the right-hand side circuit. And these are the equations that fully describe the operation of a circuit containing mutual inductance.